Hi everyone. Today we're going to have a look at parallel and perpendicular vectors and vector equations of lines. So, two lines are parallel, we know this from 2D vectors, if the angle between them is 0 degrees. So if they're going in the same direction, or 180 degrees, so opposite directions. For the vector equation of a line, we're looking at their direction vectors and the angle between those. If two vectors in 3D space are perpendicular, then the angle between them is 90 degrees, meaning that the dot product is 0. It is not technically perpendicular if the two lines don't intersect. So we also have what we call skew lines, which are two lines that are not parallel, but they do not intersect in 3D space. So if you have two lines where their dot product is 0, so the angle between their direction vectors is 90 degrees, but they don't actually intersect at any point, then you have to note that. But that would be extremely rare. So that's parallel and perpendicular vectors and equations of vector lines. To work out a point of intersection of two lines or two vectors, we just equate the x, y, and z components, and then we find the values of the parameters that we need to sub in to find the point of intersection. So we do that with simultaneous equations. Let's have a look at a few of these. Example 1, we're going to find the value of n given vector v is, as shown, is perpendicular to vector u. So we know that for the vector equation of a line, we have a point that it goes through and a direction vector to which it is parallel. So, if these two vectors are perpendicular, that means they're direction vectors. So for v, it is 2, 1, 3, and for u, it is 2, n, 1. The angle between those direction vectors must be 90, meaning that the dot product is 0. So, 2 times 2 is 4, 1 times n is n, 3 times 1 is 3. So the dot product is 0, and we can see from this that n must be equal to -7. Nice and simple. Dot product of the direction vectors will be 0 if the two vectors are perpendicular. Second example, we're going to show that these two vectors in component form are parallel. Now you could just look at these and see that one is a negative multiple of the other. I'm going to show you the long way in case you ever need to use it. So I'm just going to write these as, or in vector form, just because it'll make my notation a little bit neater. You certainly don't have to. But I'm going to call these u and v. And you could at this point just say, well, if I bring a lambda out the front of that, or a -2, I can see that one is a multiple of the other, they are parallel. But what we're going to do is find the angle in between them. So we know that cos theta is equal to u dot v over magnitude of u times the magnitude of v. So I'm going to work a few things out over to the side and then sub them in. The dot product, well, I've got 1 times -2, which is -2. 2 times -4 is -8. -1 times 2 is -2. All of that gives me -12. The magnitude of u is the square root of 1 squared plus 2 squared plus -1 squared which is root 6. The magnitude of v is negative 2 squared plus negative 4 squared plus 2 squared, which turns out to be root 24 or 2 root 6, as we could have predicted. So let's put some of these numbers in. Cos of the angle in between the two vectors will be u dot v, which is negative 12, over 2 root 6 times by root 6. So cos theta equals negative 12 on 12, or negative 1. From there I can say that the angle in between them will be inverse cos of negative 1, or 180 degrees. So these two vectors are parallel, just going in opposite directions. That's a long way. You can just show that one is a multiple of the other. Okay, let's have a look at points of intersection. We're going to find the point of intersection of these two vector lines. So I'm going to do that by equating my components. So I'll start with the x components. I've got 3 plus 1 lambda, which must be equal to the x component of my other line, 3 minus 2 mu. And at this point I'm just going to rearrange that so I can have a nice neat expression for lambda if I take away 3 from both sides. Now I'll look at the y components, and because we only have two variables, lambda and mu, we won't actually need our third equation in terms of z. So you can look at these to begin with and decide which two components out of x, y or z look easier to perform the arithmetic with. Often it won't make that much of a difference, but that option is available. So the y components for u, I have minus 1 plus 2 lambda equal to, for v, minus 6 plus mu. I'm just going to add 1 to both sides. And then I'm going to sub in my expression for lambda, which I got from my x components. So I've got 2 lots of negative 2 mu equals minus 5 plus mu. I'm going to write out all the working out. You certainly don't have to. Minus 4 mu is minus 5 plus mu. Minus 5 mu is equal to minus 5. So mu must be 1. And if mu is 1, well that means lambda, which is negative 2 times mu, must be negative 2. So that is what the parameters are equal to at the point of intersection of these two lines. So let's sub into u. So I'll get 3, negative 1, 7, plus lambda is now negative 2. 1, 2, 1 was the direction vector. And I just need to work this out. So 3 minus 2, get minus 1 minus 4, 7 minus 2, give me the point of intersection of 1, negative 5, 5. If you really want to, you could also check vector v, or line v, just to make sure that you're on the right track. So we'll do that now. V was 3, negative 6, 2, plus mu is 1, so we're just adding the direction vector. And I get 3 minus 2 is 1, minus 6 plus 1 is minus 5, 2 plus 3 is 5. I get the same thing. So that verifies that my point of intersection is 1 minus 5, 5 in 3D space.